Okay, I'm going to demonstrate how sampling frequency can be visualized in Audacity. So here are our options as far as sampling frequency. Now you might think, why in the world would you need to sample at 384,000 times a second if we can only hear up to 20,000 hertz, which using a 44,000 sampling frequency would cover all the frequencies that we can possibly hear. There are some people that think that even though we can't hear that high in frequency, that using higher sampling frequencies makes the signal better, right? Has more fidelity, okay? It captures more of it. Now remember, the relationship between sampling frequency or digital signal processing parameters and memory or function, more samples you have, the more memory, the more computations it takes, the longer it takes, and all of that. But let's do this. We'll do an 8,000 hertz sampling frequency, so your Nyquist would say that up to 4,000 hertz you can represent accurately. So let's go generate tone, 500 hertz, 20 seconds. Okay. And the sampling frequency is 8,000 hertz, and you can see that. Now let me mute this. Let me click out of it. You have to just click, so if you want to do this on your own. Now we're going to create another one. Maybe. It's not letting me click on it. There we go. Let's make another one at 44,100. Let's go to generate tone. And keep everything the same, 500 hertz, 20 seconds. Alright, now let's look at these. Okay, so I'm going to mute that, mute this one. Actually, I'm going to have them both unmuted. I'm going to click and drag down and then to the right to highlight a section. And then I'm going to zoom into that section. I'm going to keep zooming until, right there you can see the fine data, same frequency. The only difference is the sampling frequency is different. So now I'm going to zoom in even more until we can see the individual sampled points. Okay. So when you look at it, you can see that for an 8,000 hertz tone, you have using a 500 hertz tone that's sampled at 8,000 times per second, you can see the individual sampled points, right? So that continuous line we used to see is really not there. And you can see here with 44,100, so the 44K sampling frequency, you can see that there are more samples, okay? And so, and by doing so, it changes the highest frequency that you can see. Now, if you're sampling at 8,000 hertz, and you can accurately capture up to 4,000 hertz, then this 500 hertz signal will be natural. There won't be any alterations. But if you tried to make, let me see if it'll even let me do it. Let's try. I'm going to mute this. I'm going to try to make, let's see if this will work. It probably won't even let me because it's going to do the calculation. So I'm going to do an 8,000 hertz sampling frequency. And I'm going to try to generate a 5,000 hertz signal. And I would be willing to bet that it won't let me, because it's going to say your Nyquist has been violated or something. Excuse me. Yeah, see, it won't even let me do it because it's going to say, now if I take this 0 away, well, now it will. So it has some kind of built-in calculator that'll say this cannot be made because it's outside your Nyquist. So anything above, but I bet you if I change this to 4,000, it'll probably work. Yep. So then I could make that. Does that make sense to everybody? Hopefully it does. All right. So that's that's the sampling frequency. Hope that helps. I also want to show you if we go under generate noise, white noise, you can pick, we'll just use white noise for now. We'll talk about different types of noise later, but white noise, if we make a white noise and zoom in, we used an 8,000 hertz sampling frequency. So if you remember, a white noise is random, right? And here you can see the randomness to the noise, right? There's no repeating pattern. Those sampled points fall at random positions, okay? But so I wanted to show you the randomness of the white noise and what it looks like in a digitally sampled way. Now, if a white noise technically has frequency energy across all the frequencies, if you only use an 8,000 hertz sampling frequency, you won't be able to accurately represent above 4,000, right, based on your Nyquist. So I'm gonna capture a segment of this, go to Analyze, Plot Spectrum. We don't have enough data, so hold on one second. Let me zoom out a little bit here and get a little more data. Go to Analyze, Plot Spectrum. Yeah, and see, it will give you, so this is the spectrum of white noise. See, it has kind of equal energy distribution from 2 hertz up to 4,000 hertz. So notice, it doesn't give you information above 4,000 hertz because of the Nyquist theorem. It can only accurately, I'm going to change the parameters of the analysis. Now, here, rectangular window, Hamming window. So this is, you get to pick. Of course, you're not going to have to do this in undergrad, but this is showing you how it's the options you have for windows to do the analysis. Okay. Also gives linear frequency versus log frequency, and if you remember, log frequency just basically spreads out this lower frequency region, kind of condenses it in the higher frequency region. So you can see the distance between here and here is not the same as here and here, right? You have a kind of condensed high frequency region, and the low frequency region is spread out. That's the difference between linear and log, but we'll go back to linear frequency. So in a linear frequency, 500, 1,000, 1,500, 2,000, 2,500, 3,000, everything is equally spaced. That's a definition of linear versus logarithmic. Okay, hope that was helpful. I'm going to do one more thing. So remember, the white noise only has information out to about 4,000 hertz here because of the sampling frequency that we used. Let's do this. Generate. Let's use one that's 44K, 44.1 kilohertz. Let's go to generate, noise, white noise, same thing. We'll zoom in. Again, you can see the random samples. There's more of them, obviously. There's your random samples, points. Zoom back out. And now we're going to analyze it. Plot spectrum. And now you should notice that instead of having energy only up to about 4,000, which is right here and below, because we use the 44K sampling frequency, we're able to get energy out to 22,000 or 22,050 technically, because it's half. Okay. Again, here's your window options: Hamming, black, rectangular, lots of different options. But again, we use Han or Hamming the most. And I think that's good for now. Hopefully that helped you understand Nyquist theorem relating to sampling frequency, relating to maximum frequency in the output that you can have. Wanted to also demonstrate the randomness of white noise, right? and how white noise technically covers all the frequencies that you can possibly hear if you use a sampling frequency that allows you to get at or above 20,000 hertz. Okay. Hopefully this was helpful, and again, we'll chat more about it in class.